Hello, welcome to this video on Grassmann numbers in physics. So Grassmann numbers are something that is useful when talking about states of matter and particles, which are matter particles and make up materials. It's hugely important when describing them in kind of relativistic quantum mechanics or in certain branches of particle physics, such as supersymmetry. But today we're not going to be looking at them in that much depth, although I will make a video of kind of the relativistic quantum mechanics that is behind much of the motivation of using Grassmann numbers. But today we're just going to be having a look at how we can think of them just in the context of the foundations of quantum mechanics and describing matter and states of matter. So this will be an introduction to Grassmann numbers. So eventually we're going to be looking at how Grassmann numbers embody symmetries of wave functions describing particles that make up matter. But before I do this, I'll just go over some core aspects of how we describe a system in terms of wave functions using standard ideas in quantum mechanics before we introduce Grassmann numbers. So we start off thinking about a system of a pair of identical particles, and I'm calling these particles A and B. Now, clearly if they're identical, if we exchange their positions, it's not going to do anything to the overall probabilities associated with that system because they're identical. There's no difference as far as the physics of the universe is concerned. And because of this, if we have A in position 1 and B in position 2, the probability of some physical observable corresponding to that system is the same as the probability of that observable if we had particle B in position 1 and particle A in position 2. So we get the probability of AB is the same thing as the probability of BA. And that just comes from the fact that we're dealing with identical particles, so the universe cannot have any way to tell in which positions those particles are, like whether A is in position 1 or 2. If we exchange their positions, the universe is none the wiser. And because of quantum mechanics, we know that we get the probability by taking the square of the wave function. So if P of AB is the same as P of BA, then the square of the wave function for AB must be the same as the square of the wave function of BA, because probability is just the wave function squared. And to satisfy this kind of expression with squares of wave functions, it must therefore be the case that the wave function for particle A being in position 1 and particle B being in position 2 is plus or minus the wave function for particle B being in position 1 and particle A being in position 2. And this enforces that for identical wave functions, for identical particles, we must describe the system of these identical particles in terms of wave functions that have a particular symmetry. So they can either be symmetric or they can be anti-symmetric. And on this slide you can see an image showing what symmetry looks like and what anti-symmetry looks like. And for particles that make up matter, it turns out that they are anti-symmetric in terms of their wave functions. So we have a minus sign instead of the plus or minus sign. So we have talked about the fact that for particles that make up matter, when you exchange the position of the particles, you just put a minus sign in front of the wave function. Oh. So now we are going to move on to look at what this negative sign means in terms of physics. So now we've seen the anti-symmetry of the wave function of particles that make up physical matter. We're now going to have a look at the consequences of this and see how it leads to quantum particles that make up matter wanting to occupy different quantum states. So for this, we start by saying that unless we measure the state of a system, the universe will always try the system will always try to be in a state of superposition of all possible classical states in which we can measure it being, if we were to measure it. And a consequence of this is that the overall state of our system is got by simply summing the individual possible wave functions. And because we've got two particles, we've got two wave functions, and we have to add these together to get the overall wave function of our system. And it is worth saying here that when we're doing this, capital Psi represents the superposition of all possible classical states. So if you had more particles, this would have even more terms. There would be more terms in the brackets, but if you had even more classical states available, there would be even more individual classical wave functions we would have to add together. So these expressions can get pretty lengthy, but we're only worrying about exchanging two particles, so there's only two wave functions we have to consider to get an overall wave function. But we said that for matter particles, the wave function of AB is minus the wave function of BA, so we can write our total wave function as this expression down here, because psi of AB is minus psi of BA. So we've got the total wave function is minus psi of BA plus psi of BA, where psi is just the letter used to represent a wave function. And if we're taking away something and then we add that same thing, we get 0, no matter what that thing is. So the total wave function is 0. And what this means is that there is no information available within the system. And since there's no information, it can't transfer that information to anything else. So as far as the rest of the universe is concerned, it does not exist. Well, I mean the two particles do not exist. So what this means is that because of the particles being identical and the anti-symmetric nature of the wave function, the total wave function for that pair of particles is 0, but it's worth saying it's 0 providing we don't have extra considerations to consider which could indeed allow us to distinguish between A and B, such as if the particles were in different energy states, for example. It's only when there is no distinction for A and B in which the total wave function is 0. So that's worth bearing in mind. So we've got now a description of the anti-symmetric nature of the wave functions and its physical consequence. And now we're going to describe that same thing using Grassmann numbers. So in Grassmann numbers, when we're finding the total states of a system, we don't add the individual classical states together. Instead, we multiply them. So, for example, if we're taking eta to be our wave function, then the total wave function for two identical particles in the same physical state, as we've seen before, is minus the wave function of VA plus the wave function of VA. We can rewrite that as the total wave function is minus eta, which is a Grassmann number used to represent the wave function of VA, and then we multiply that minus eta by eta and we get 0. And we have to get 0 because, as we said before, the anti-symmetric nature of the wave functions, the classical wave functions, means the total wave function must be 0. So from this we can see that a defining feature of the Grassmann numbers is that a Grassmann number multiplied by itself must give me 0. And so we can kind of generalize this and say that a Grassmann number raised to any integer power bigger than 1 must be 0, because, for example, eta cubed would be just eta times eta times eta. But since eta squared is 0, eta cubed would be 0 times eta, which would be 0. So Grassmann numbers are nilpotent. If we raise it to an integer power bigger than 1, we get 0. When we use Grassmann numbers, we replace the wave function, which describes the state of our system, by a Grassmann number, and we replace the idea of summing to find superposition states to multiplying to find superposition states, and then the symmetry of the wave function enforces the nilpotent property that defines a Grassmann number. Now, I could go into a lot more depth, and you only really need to start using Grassmann numbers in supersymmetry, and it's very handy in kind of quantum field theory when talking about particles that make up matter. It is also worth saying that when I say particles that make up matter, I mean a lot of the fundamental or nearly fundamental particles, such as nearly fundamental ones are like protons and neutrons. They're nearly fundamental because they act essentially as a single particle for the most part, but they are actually made up of quarks, and quarks are fermions and have anti-symmetric wave functions, as do protons and neutrons. But things like atoms, which are very clearly not fundamental nor nearly fundamental, they're made up of particles doing very different things, which are physically spread apart in space. In that case, the atom is not necessarily a fermion. In fact, it generally would not be a fermion in a lot of cases. So it is worth saying when I say particles that make up matter, I am really talking about fundamental or nearly fundamental particles. But anyway, this has been an introduction to Grassmann numbers, and I'll hopefully make a video in the future describing the role of Grassmann numbers in quantum field theory, or in a more relativistic setting than we have here. Thank you very much for watching, and hopefully see you for another video soon.